Good morning students. We will continue the previous class. In that previous class I was saying you about the spherical refracting surface. A refracting surface which forms a part of a sphere of transparent material is called as a refracting surface. Just you look here. Here this curved surface. This curved surface, I mean this is like this. Here behind this curved surface you can imagine one sphere. Okay, below, I mean behind here you can imagine one sphere like that. You see behind this curved surface here there is an imaginary sphere which I represented with red dotted lines. So I mean this curved portion looks like a part of this imaginary sphere of transparent material. Similarly, look here. This inward curved surface, inward curved, I mean it is like this, I mean it is like this, inward curve, like this. Okay. If you see here, look on this one, here also you can imagine one sphere. It is curved like this. Here you can imagine one sphere, solid sphere of transparent material. This curved surface looking like a part of this imaginary sphere of transparent material. This surface we call as a spherical refracting surface. Here it was like this, here it was like this. This side we imagined one sphere. This looks like a part of this imaginary sphere. So we called this as a spherical refracting surface. And here when you look on this second diagram, it is looking like this. This side we can imagine one sphere. This is sphere of transparent material. This is a part of that. So this we call as a spherical refracting surface. Okay, a refracting surface which forms a part of imaginary sphere of transparent material called as spherical refracting surface. These spherical refracting surfaces mainly classified into two types. One is convex spherical refracting surface and another one is concave spherical refracting surface. Convex and concave means what? You see here. First of all, you should know this convex. Convex surface means what? It looking like thick at the middle than the edges. From here to here it is one surface which is available for refraction. Even this surface which is available for refraction we call as an aperture. This is aperture. From here to here, I mean from this point to this point. This curved surface is available for refraction. This we call as aperture. The geometrical midpoint of this aperture, geometrical midpoint means what? From here to here, their midpoint. This midpoint we call as a pole, P-O-L-E, pole. The geometrical midpoint of that aperture called as pole. Yes. Now you look here, what I mean to say. This one. Okay. Like this. Convex means thick at the middle than the edges. At the edge, you see this surface somewhere middle. It looks like bulged. I mean, it looks like thick at the middle compared to edges. It called as convex. Concave means what? Concave. You are here this side. I mean, see that. Concave means it looking thin at the middle than the edges. This specially you will be going to understand in the section called as lens. There you will be getting two types of lenses. Lens means that also an optical medium. There also you will be getting convex lens, concave lens. There you will be finding like this type. This is a lens. Lens means an optical medium bounded by two surfaces of which at least one should be spherical. Here in this one, both surfaces are spherical. Both, this is one side and this one is another side. Both are spherical. They are thick at the middle than the edges. This is edge, this one and this one. Thin at the edge, thick at the middle. This kind of arrangement is called as convex, thick. Getting? Concave means what? Like this. Imagine. Like this. Here, okay, thin at the middle, thick at the edge. Thick at the edge, called as concave. See, concave means it looks like this side. If you weaving this side, it is inward bend. If you weaving from this side, it is inward bend. This is concave, and this is that side, convex. See, now here, convex refracting surface and concave refracting surface. Which is convex? Look, if that refracting surface is convex towards the rarer medium. Here, this side, that transparent sphere, that side air medium is there. So that is air, and this one is that glass. It may be transparent glass. It is glass. So that air is rarer and glass is denser. Getting? Now, rarer medium, denser medium. Here C is the center point of that imaginary sphere. Center point of that imaginary sphere. Even we call it as a center of curvature. C point we call as center of curvature. Then the distance between that pole and that center of curvature, this we call as a radius of curvature. You see here, this is a sphere. This pole is a point on the circumference. Distance between that point on the circumference to the center we call as radius. Now, the distance between this pole and center of curvature, this distance we call as radius of curvature. These things we should know. Now you see, rarer that side, denser is this side. Convex means if that refracting surface is convex towards the rarer medium. Convex towards the rarer medium means what? Towards rarer medium, it is thick at the middle. Towards rarer, if it is thick at the middle, I mean it is curved like this, then it is called as convex spherical refracting surface. If it is convex towards the rarer, means if it is thick at the middle towards the rarer, then it is called as convex refracting surface. Here it is. Concave means if that refracting surface, this one from here to here, if that refracting surface, this side you see here, imaginary sphere is here. Here rarer medium is there. This side denser medium is there. Getting? Now you see here. If that refracting surface is concave towards the rarer medium, concave means I said, this side right now air is there. This is a rarer medium. Concave towards that means what? Should be thin at the middle. Somewhere at the edge it is thick. Thin at the middle. I mean it should curve like this. Here towards this. This is called as concave towards that rarer medium. Then it is called as concave refracting surface. Okay. So now there are two different types. Those are convex refracting surface and concave refracting surface. After that, After seeing those two, now here there is a very important derivation there. Means what? Here we are going to derive one expression which is going to relate the object distance, image distance, and refractive index of the medium through which light ray is moving to produce the image. See here, it is very important derivation and equation, or equation, which is going to relate the object distance, image distance, and a radius of, and not radius, refractive index of the medium. See here, it's a 5 mark, very important derivation. Look here on the title. I have written refraction at a spherical surface. Refraction at a spherical surface. Look on this diagram. Here we have taken convex refracting surface. Convex, this one. This is a convex surface like this. Here imaginary sphere is there. That sphere has its geometrical midpoint called as center of curvature. This C is the center of this imaginary sphere of transparent material. So that we call as denser medium of refractive index N2. Around this imaginary sphere there is a air medium there, which is rarer compared to this one. So that we call as rarer medium, air, with a refractive index N1. N1 to the air and N2 to the denser medium, to the glass. So now you see here, this surface is convex surface. This is center of curvature. Already I said that curved surface which is available for refraction called as aperture. Their midpoint, this point, we have to call as pole. This is pole. Midpoint of that aperture, it is pole. Now, a line, a horizontal line which is passing through the pole and center of curvature is called as principal axis. A line which is passing through the pole and center of curvature is called as principal axis. This dotted line is principal axis. Now you see here in this diagram. Here O, this O is an object which we place in front of this convex surface on the principal axis at a distance u. Already we discussed all the distances we have to measure from pole or optical center point. Here it is curved surface, so being with the pole only, this is pole, we have to measure distances, object distance, image distance, all distance we have to measure from this point. Okay, yes, from here to here, this is object distance. So I mentioned it with a small letter u. Okay, yes, let O is an object placed on principal axis at a distance u from the pole. Okay, yes. Now see here, we placed the object in denser medium. We placed that object in rarer medium. Their image we going to get in denser medium. Just look on this ray diagram. We call this as a ray diagram. Yes. To get image, at least we should take two refracted light ray. Where they going to intersect or they going to meet, there they going to produce the image of that respective object. Let look on that object. Let ON is the light coming from that object. This light. ON, this point I named as N. Here N is not normal, just a point. ON is incident light. That light came from that object and got incident on that curved surface at a point N. Yes, to that point N, we have to draw one normal. Yes, this is a curved surface, has a center point here. To that point, normal means obviously that line which is going to meet at the center, looking like normal. This line, this dotted line is the normal to this point of incidence N. Yes. Now, this is the angle of incidence. This is incident light ray. Yes. That ON light is moving from rarer to denser. Obviously, instead of moving straight, it is going to bend towards the normal. Yes, it bent inward because it entered into denser medium. Their speed got decreased. That's why that light ray bent towards the normal. This light. Yes, ON and NI. That light ray, it came and it just got incident on that principal axis somewhere here. It crossed that principal axis here. Yes, this is one light ray. This light ray moved like this. Fine. It came like this and propagated along NI path. One light ray. Let's take one more light ray. This light. That also coming from that object. Look on this light ray. This is coming and going to hit that curved surface at a pole point. Means what? This light ray, okay, got incident at this point normally. Yes, if you further extend this line, it is going to meet at center point. Means this is radius. Obviously, this point. Okay, now this line is perpendicular to that point. Means what? This light is going to get normal incidence. Because of that normal incidence, this light ray keeps moving along its path only, along their initial path only. It moving along the principal axis. Yes. This one and this one. These two are the refracted light rays. See here, this light ray is coming somewhere here. Yes, here at this point I. At point I, both refracted light ray got met. Where a refracted light ray are going to meet, there they are going to produce the image. Yes. Now here at this point I, there is an image. There is an image of that object O which is placed in rarer medium. Object placed in rarer medium and image we got in denser medium. Have you understood? It's very important. Later after completing the derivation I will tell you why I said this more. See now, here this is image. Okay. Here from this pole we to measure their distance. Yes, this distance is image distance that I named with the small v. Small v is the image distance, small u is the object distance. Then one more distance is there here that we call as a radius of curvature. From pole to center of curvature, that distance we call as radius of curvature. Even this distance also we have to measure from pole like this. This is R, radius of curvature. This image distance we have to measure in this direction. Object we have to measure in this direction. All distance we have to measure we have to measure from pole point only. Have you understood? Yes. This is about diagram. See here. This is a refracted light and this is normal. Now this angle we call as angle of refraction. R is the angle of refraction. Then you have to draw one normal from that point N to that principal axis. From this point N, you have to draw one perpendicular line to this principal axis. Okay? Yes. After this diagram, with the help of this ray diagram, now we are going to get the expression which is going to relate these object and image distances and refractive index and radius of curvature. Okay? Yes, that relation now later we are going to get. Now see here. Now we go with derivation. See here. Concentrate. From triangle NMO. NMO. Here there is one triangle. Right angle triangle. And triangle NMC. NMC. And triangle NMR. Three triangles. NOM, NMC, NMR. These three triangles. From these three right angles, all those three are right angle triangles. From those three right angle triangles, we can write. To the right angle triangle only we can apply trigonometric functions. Okay? Yes. Here you can change it, that symbol, right angle triangle. Here I have written triangle symbol, even you can make it a right angle triangle symbol. Yes, alright. From these three right angle triangles, we can write. What we can write? Just you see. I have taken tan function. There are 6 trigonometric functions are there. Now among those, we using tan function. Tan of any angle is equal to opposite by adjacent. Tan of NOM in this triangle. Look on NMO triangle. NMO this triangle. Okay? Look on this triangle right now. Angle NOM. I mean to this angle. Tan of this angle is equal to opposite by adjacent, which is opposite to this angle. NM is opposite divided by adjacent. OM is adjacent. Have you understood? Yes. Similarly, in this right angle triangle NMC, this triangle. Look on this one. NMC. Apply tan function to this angle. Tan of NCM to this angle in this triangle. Tan theta is again opposite by adjacent to this, which is opposite. NM is opposite, adjacent is MC or CM. See that tan of NCM, tan of this angle is equal to opposite by adjacent. Opposite is NM by adjacent is CM. Okay? Yes. Next, finally, look on that right angle triangle NMI. Now apply to this angle. Tan of NIM, tan of NIM, again opposite by adjacent to this angle, which is opposite. NM is opposite, NM by adjacent, which is adjacent. MI is adjacent. NM by MI. Yes, here. I mean, to those three right angle triangles, we have taken tan function to those three three respective angles and we got their values like this. Okay, yes. Now for triangle NOC, look here, it is very important. For triangle NOC, this is N, this is O and this is C. This triangle. For this triangle, is this eye looking exterior angle? Yes. Look on this one. To this triangle, this eye is looking an exterior angle. What is a relation there? If that angle is exterior to the triangle, then that exterior angle is equal to the sum of opposite interior angles. That exterior angle to the triangle is equal to the sum of opposite interior angles. Here it is there means leave this. Opposite means these two angles. Opposite means these two angles. That exterior angle is equal to the sum of opposite interior angles. That is equal to angle NOC. Angle NOC plus angle NCO. Getting? Yes. That equal. In place of NOC, have written NOM. Why? You look here. NOC and NOM both are same angle. NOC, NOM, this angle only. Both are same. NOC I replaced by NOM plus NCO. NCO I replaced by NCL. See this angle. NCO is equal to NCM. That's why I replaced NCO by NCM. Okay. Then that equal to. Previously we got their respective values. NOM. Here angle NOM is there. That is nothing but we treated as NM by OM. NM by OM plus. Okay. Next to NCM there. NCM. Okay, NCM, that is nothing but NM by CM. NM by CM and this is NM by OM. Okay, one thing will arise here. Sir, here only angle there. There we been with tan of that angle. Yes, very, very important. When we go, see with the small angles. When we go with small angles, to that small angle, if you apply tan or sine function, okay, tan of small angle is equal to that angle only. I mean tan of theta is nearly equal to theta. Sine of theta is nearly equal to theta. When it is, when that theta is very small. I mean for small values of theta, tan of that theta even nearly equal to theta. Sine of that theta is nearly equal to theta. That's why here we have to imagine that angle is small. So we treated tan of that angle is equal to that angle. Tan of NOM is equal to angle NOM. On that way we treated, so we been with that directly here. Have we understood? Yes. Here NOM we treated as this one, NM by OM. NCM, NM by CM. Call it as equation 1. Equation 1 giving the value for angle of incidence. That I is equal to this, that is equation 1. Yes. Now after this, for triangle NCI, look on the diagram. NCI. Where is N? Here is that. NCI. For this triangle. For this triangle, is this angle looks exterior? for this triangle. Okay.